3D NAND. The talk is going to be pretty much focused on 3D NAND, not on some of the emerging memories, but I would like to lay a little bit of foundation for the speakers coming after me who are going to talk about different emerging memories as well. I'd like to cover a little bit on the NAND market itself and what has led to this transformation of going from a planar NAND to a 3D NAND, and how the roadmap is going to look like moving forward in terms of a vertical NAND scaling. If you look at the memory market right now, how it's transforming, 5 or 7 years back, you don't even have to go a decade back, most of memory was being dominated by the big OEMs. You look at the memory landscape, we were supplying primarily into the compute industry, and the big OEMs yielded a lot of power, and there were many players, both from the industry supply-wise as well as memory manufacturing-wise, and most of the innovation was driven primarily by Moore's law scaling. It was shrink, shrink, shrink. That was the direction that the memory industry was going in. But in the last 5 years, as you look at the transformation that's happening, the number of customers have exploded significantly for memory manufacturers. We have the traditional server individuals who have racks and racks of servers, but a lot of the new players like Google's and Facebook, they now have their own server farms, and 5-10 years back they were not your primary server customers. And with the explosion of big data, Internet of Things, all the connectivities that we are looking at, there's been an explosion in the number of customers that you're seeing, and each one having their own unique set of requirements. But at the same time, the memory industry is consolidated, both from the manufacturers as well as the equipment side. So on one hand, the customers have increased, but the suppliers have reduced. And also we are starting to hit certain limits in terms of scaling. There are some physics-based limitations we are hitting, as well as materials and technology limits. So when you take all of this, memory has taken a bigger transformation, and what used to be a commodity silicon supplier is now starting to become a more niche solutions provider instead of just a commodity. So in this graph, what you're looking at is moving from a base silicon chips provider into a final end system solutions provider. With that transformation, it's no longer just a scaling path. Memory can provide solutions through packaging, through controllers and firmwares and softwares. So eventually you're looking at providing the end solution and not just providing a commodity chip to a customer. That's a big transformation that's happened within the last decade with memory. And most of the significant technology trends that have driven to this transformation are these top 5 in our opinion, which are big data, cloud, networking, the machine-to-machine, or a lot of the data sharing that's happening, and mobile. The significant increase in mobile has changed how memory is seen as a solutions provider, but also the demand for memory has significantly increased. And in particular, flash. When you look at flash memory, it's starting to play a big role in mobility. And that's also enabling a huge number of applications that's driven by this mobility increase that we are seeing. When the storage market comes, there are 5 big things that's happening. With enterprise, when you look at it, a lot of focus is being placed in terms of reliability and fault-free systems. So wherever you have moving parts, like hard disk drives, that are getting replaced by mostly flash-based solutions. So any active data is getting moved into flash, and all of the inactive data is in the cloud. And the focus on reliability and fault-free data storage is where the enterprise systems are moving, and that's driving a huge increase in flash consumption. The same with the data centers. Data centers are starting to become lights-off data center right now. With that, there is an increase in the requirements for flash, and many flash-based platforms that we are able to provide as the end solution. That has changed the demands for flash serving to the data center. And then as customers and looking at the client portfolio, flash has really enabled all the SSDs that we are looking at, has enabled the ultra-thin laptops, to all the mobile devices that we are using, to gaming. The gaming industry is a big consumer of flash right now. And all of this is enabled as flash is continuing to maintain its low-cost position and as a non-volatile memory. When you compare the DRAM to the NAND, NAND definitely has its own performance disadvantages compared to DRAM, but it is the lowest cost memory, and that's where the storage solutions are continuing to be switched off my phone, so I don't know what that is. Anyway, that's where the storage solutions are coming in, is these four big areas that you're seeing: enterprise, client, data centers, and also all of the consumer consumption. All of this, again, has increased the NAND demand. And this is the NAND demand curve that we are seeing right now. It continues to grow. There's a significant explosion in the number of NAND bits that we are starting to require in terms of the end market application. But at the same time, the supply growth has been steadily decreasing. If you look at a decade back, we were in the significant 100% growth rate year over year for the bit growth that the industry was able to provide. And then in the last decade, that has slowly dropped into the 30s to 40% bit growth year over year. This decline is primarily from technology scaling issues that we are seeing. You can only scale so far, so as you are continuing to scale the dimensions, it's starting to have lower return on your investment. And for continuous bit growth, you can approach it in multiple ways. One, the continuous technology scaling. In terms of planar NAND, that's what we have been doing, and we can continue to go down the 1Z, 1Z prime, all of these, continue to shrink towards the 13 nanometer devices. But as you are continuing to shrink 16 or 13 nanometer, the return in the amount of bit growth versus the capital that you have to put to continue to shrink is not very advantageous. That's where the planar shrink is starting to have its own limitations. Well, the other way to get your bit growth is you can change your wafer size, and that has economics issues. Or you can just go build more fabs. Again, there's a return on investment issues and the economics, and that cannot be the only primary path. And that's where you're starting to see a significant increase in disruptive changes that we are seeing in the memory industry. Either you're starting to go towards crosspoint or stacked alternate architectures, or something like vertical NAND, where you are taking the physics challenges and eliminating them and continuing to provide the bit growth that you need to meet the market demand. And that's what I would like to talk a little bit more about, is from a NAND perspective, what are the challenges that we faced with the 2D NAND and why we had to go to a 3D. This is the graph that really shows over the technology nodes what the cell size has been scaling to. And the scale size continues to scale down, and at some point you're not going to see the benefits in terms of bit growth. You can only do so much with your periphery shrink, and then the array shrink is going to start with its limits. In particular, with the floating gate cell architecture, we have the control gate and the floating gate. And as you're continuing to shrink, the physical space available for you to go deposit the floating gate is just not existing. It's the same in a DRAM case where you're looking at capacitor dimensions. Here in the floating gate dimensions, you don't have any space to go deposit the gate that you need to store your electrons in. And as a result, what happens is the physical space shrinks, and you can only store so many electrons, and the number of electrons that you're storing right now is so limited. They are starting to know each other in a first name basis. You have like 5 or 6 or 7 electrons that you have to control now, and that's not possible to control very efficiently. That's one of the big challenges that we face in terms of physical limits. But also with electrical limits, as your size and scaling shrinks, your VT window starts increasing. Especially as we are going from a single level cell to multi-level or a triple level cell and maybe even a quad level cell, you don't have enough margin because your VTs start merging between the different cells. So that's your electrical limitation in terms of continuing to do a planar scaling. And there's a lot of debate about, okay, what happens if the planar scaling stops? Are we not going to have more transistors? Well, that's not the case. We are going to continue to shrink or continue to increase the density, and that's where you're looking at 3D NAND. In order for Moore's law to continue, more from the perspective, not from a shrink perspective, but from the perspective of increasing density, 3D NAND is essential because planar is going to hit its limits. And this is a graph that kind of explains that, where you are looking at effective cell feature size to the physical cell feature size. So with a planar NAND, you're on this linear drop down where as you are continuing to change your cell feature size to get more density on a wafer, your physical cell feature size hits its limits. And that's where you're not able to continue to shrink. But in the case of a vertical NAND, as you are taking all these bird lines and stacking them down standing tall, you can get to an effective cell feature size shrink, continue to do it, but you're able to maintain a much higher physical cell size. So you're no longer limited by the physical cell size, and you're going to be limited more by how tall can you stack. That's going to be the limitation. When you look at the number of electrons compared to a 2D NAND, that's going to be on this linear scale of continuing to decrease. On a 3D NAND, since you're no longer limited by your physical cell size, you can have the same number of electrons. You can continue to scale your cell size, but your physical size is not limited, so you can have the same number of electrons. What does that mean? That means you can continue to scale in terms of your TLC and your cell performance and your reliability can continue to scale as you're adding more and more density to the die, because your physical cell size is not limited. On a cost perspective, this particular graph depends on what application and what density you're looking at. But there are certain densities where the planar NAND, in terms of the return on investment as you're continuing to shrink, it's not going to be high for you to get a continuous cost per gigabit decrease. So if you're not going to be on a 30-40% cost per gigabyte decrease generation over generation, then you're starting to question, why am I doing this node? What's the benefit? And that's where vertical NAND is going to be on a path where you can continue to scale vertical NAND, put more densities. You're not sacrificing the performance of the cell, and you're going to be able to continue to drive a lower dollar per gigabyte. The same in terms of total gigabyte per centimeter squared. You get a much higher increase in gigabyte per centimeter squared with vertical NAND compared to the planar NAND. And as I showed, there are a lot of challenges in scaling, but this is a path we think we can stay on for the next several generations. And the last one is on the electrical performance compared between 2D NAND and 3D NAND. I talked about the VT distribution grid. How as you're shrinking in the planar, you're getting into a regime where you have very few electrons and your VT distribution width is broadening, that you have signal to noise issues. But in the case of a vertical NAND, you can maintain a pretty tight distribution. Even as you're scaling the densities, since the physical size is not scaling, you can have a very good reliable performance on multi-cell level performance with 3D NAND. So recently Micron and Intel announced the 3D NAND. This is a different architecture from some of the other alternate architectures out there. Everything has its pros and cons, but the architecture that we have, we believe it's going to serve into different 3D markets, and it's going to have a significant cost advantage because of the density with which we are going. It's going to have a significant capacity increase in terms of total density on the wafer and the performance-wise. So the confidence from a customer in terms of performance is going to be very good, because now you have relaxed the cell size, the physical feature size, so you don't have interference and other concerns that you would see with a continuously scaling planar NAND. So what's needed for vertical NAND scaling? This is a big question out there. We are starting with a certain number of tiers, whether it's 2x or 3x. How high can you go? And where do you see the limits of vertical NAND starting to have issues? What I wanted to show here is, at least at this point, we see vertical NAND continuing to scale. So there can be several generations of vertical NAND that we clearly see in the future. There are several ways you can scale vertical NAND. One is the number of tiers, and as you're scaling the number of tiers, you're just going to add the total height, but the density scales linearly. The other one is your pillar CD. You can put more pillars in the particular stack that requires your pillar CD to scale. The other way to scale without impacting the aspect ratio too much as you're scaling more tiers is to actually change your each tier stack height. That means your word lines, you're shrinking in the vertical direction. But that then brings more issues with respect to resistivity and other concerns, because now your word line metal is starting to shrink. But that's another path. And all of this are going to present a challenge in terms of aspect ratio. That is outright the biggest challenge as you're starting to scale in the vertical direction. So I've shown a few key challenge points here. One is the tier stack scaling. When you look at tier stack scaling, it's all with respect to aspect ratio. You're depositing these thick materials, it's going to have stress issues. And as you shrink the CD and you're stacking more and more layers, you're increasing the aspect ratio. So what's going to be the limit on the edge? At what point does edge break down in terms of the aspect ratios that you can achieve? But then, as you're increasing these skyscrapers height that we are building, we are also depositing thin layers into these holes. And conformal deposition of these thin layers inside these tall aspect ratio structures is going to be a big challenge. Hard mask. With the high aspect ratio, you're starting to look at new hard mask requirements. If you're looking at a 2 micron or a 4 micron or 8 micron tall stack that you have to etch now, you cannot use conventional hard masks because they themselves are now in the 2 or 3 microns. So your hard mask height itself is 20% or 30% of your total stack height. So you need new materials. Are we going to look at metal hard masks? Are we going to look at doped hard masks? Hard mask scaling is going to be a big challenge in terms of enabling a high aspect ratio edge. The staircase contact scaling, this is where you are dropping your contacts to go connect to the word lines. It's a big challenge with respect to gap fill, because now you're starting to look at increase in stack heights of 8, 12, 16 microns. You have to fill this gap with a flowable material or some type of material. And what happens as further thermal treatments are subjected to this wafer, you can see this material shrink. And when you have a huge amount of oxide or some gap fill material and you subject it to thermal treatments and it shrinks, you can create huge stretch issues. So you can start to see the wafers bow and cracks start forming. Those are some significant challenges that we are aware of in the back end, but we have never talked about similar challenges in the front end. That's what's happening as you're continuing to scale 3D NAND. A lot of the back end type challenges are starting to come up into the front end regime. Lithography, it's not about resolution anymore because your pattern sizes and feature sizes are much bigger. So you can print them easily, that's not the question. But the bigger challenge with lithography is as the wafer shape changes, what are going to be the overlay impacts? How are you going to chuck them? Can you now see through these tall stacks that are 14, 16 microns tall? How do you align to these wafers? Those are going to be some of the lithography challenges that we face. This is what I talked about earlier in terms of gap fill challenges, where you have different features on the same wafer, but these are macro scale features. You can have cracks forming or outgassing of the material. As you're subjecting the material to higher temperatures, you can outgas and create other issues within the gap fill solution. And one of the big problems is planarization. Planarization challenges is going to actually limit 3D NAND scaling, or you have to find alternate ways to planarize. So you can think of these tall stacks that you're gap filling now with some oxide or any material, and then you have to remove the overburden of material. That's now 14, 16 microns of overburden. You cannot do conventional CMP. You have to go look at alternate methods. You're starting to talk about grinding or lapping or any completely new ways. Again, what's used in backend, you're starting to look at them creeping into a front-end type application. So those are some of the big challenges that's going to limit how high you can go, especially when it comes to planarization of within die non-uniformity. It's going to be a big challenge. And outside of all of those, it's the manufacturability challenge. So I can keep stacking 3x, 4x, or 6x, and we can solve all the process issues. But the time it takes to deposit these materials, finish the integration process, it's a pretty long flow. Or the time it takes from the tools are pretty long. So you're going to have more tools in the fab to create the same number of wafers. Or a fixed footprint of the fab is now going to create less number of wafers because it takes too long to process these wafers. So it's going to be a big manufacturing challenge, and meeting the cost of ownership is going to be a big challenge as well. On the inspect and metrology, you can think of this as now you have taken a word line and all these high aspect ratio structures and stood them up in a vertical direction. So what you have done is created an even higher aspect ratio structure, but in some cases created embedded defects because it's now inside the structures that you cannot see. So with respect to defect metrology, one of the big gaps that we see is resistive contacts. So as you're etching these tall aspect ratios, if they are under-etched or over-etched, you might be able to see them. But if they are marginally under-etched, then you cannot see. It's a resistive contact. And there's no voltage contrast method or electron beam method that can actually accurately predict under-etched contacts that are just resistive in nature. And these are big problems when you're talking about millions of these contacts on a given die. How do you predict some of these under-etched contacts that are resistive in nature that might fail later in the process flow? The other big issues are OCD and modeling issues. We have aspect ratios that are going to range into 70 to 1 to 100 to 1 in future. How can you measure not just the top CD, but also the bottom CD and the max CD? As you get bow from the edge, you have to be able to measure what is the max CD in these structures. And today, a lot of the modeling softwares that we use or the optical capabilities are not good enough for us to be able to go measure accurately the 3D NAND line. So in many cases, the only signal for 3D NAND today is from electrical signal or a destructive technique that you're using. That's going to be a big challenge for scaling. And this concept has been out there, just it looks like it's going to be something that we need to explore more and make it into a reality, which is what we are calling hybrid metrology. When you cannot measure directly certain features, how can you go and still get enough inline signals to give you good visibility into the quality of the wafers that we are processing? Either it can be indirect inline metrology, or the tools that we use have a lot of signals coming out of these tools. Can we do fault detection with these signals and connect them to some of the product measurements? Or modeling, which is predictive analysis, taking all the data that exists today and being able to predict based on the tool signals what this wafer is going to look like. Some of the destructive analysis just for correlation, how do you get them? We could use some inline fib and those measurements, and eventually the electrical signature. But how can you take all these different tools available to us to be able to put them together and get a pseudo measurement that gives a good visibility on the inline quality of the wafer? That's going to be a big challenge. We have several of these techniques available to us, but how can we put them together to get to a composite metrology solution? That's going to be a challenge facing us. And then the materials challenge. I talked about how the processing times are going to be longer as you're stacking more and more, and that leads to more wafer cost. But there is certain capital cost that we are always focused on. The focus needs to also be now on materials cost, as well as enablers from materials. How can we take certain materials and now enable a faster deposition rate? How can we take certain materials and enable a better step coverage in this high aspect ratio? The tool is going to be the same, but how can materials and precursors and gases now enable us to continue to extend the vertical NAND? That's going to be a big scope for improvement as we look into the future. And the equipment piece I already talked about. The big one is the control capability. Looking at it as a holistic approach, including the signals coming out of the tool, that's going to be a big area for improvement as we move forward. Now that's from a 3D NAND. I talked through how NAND is changing in the market, how the demands are increasing and our bit growth is slowing down, why 2D NAND is not conducive enough for continued shrinkage, and why the industry is moving to 3D NAND, and what are the challenges we are going to face to continue to overcome so that vertical NAND can have a roadmap. If you look at the memory continuum today, on one end you have the DRAM, which has a great latency performance. On the other end, you need the hard disk drive, but you look at SSDs, which are flash essentially. They are the lowest cost, but they have the worst latency performance. So you have these two spectrums where you have a non-volatile memory that's used as a storage or removable media, any type of storage devices, but has the worst latency. So it's only for storage performance, and then you have the DRAM performance, which is very good in latency, but the cost is high. And then you have this gap in between. That's where we are starting to see more and more of these storage class memories come in. When you look at any of the emerging memories, whether it's a resistive memory or a spin torque based or magnetic based, phase change based, all of these, the immediate question is it going to replace NAND or is it going to replace DRAM? In our opinion, it's not going to replace either one of them. There is actually a room in the middle where we are looking at these storage class memories with improved latency that's better than NAND and cost that's going to be better than DRAM. So you can now look at this new memory classes that's going to start emerging. They might displace a little bit of DRAM and some market share of NAND, creating this new storage class memory, but they are not going to completely replace either one of them. Because the cost-wise, when you look at it, NAND is still going to be the lowest cost solution provider because of vertical NAND. Any of these emerging memories, for them to be low cost and compete with NAND, they have to get into the vertical model as well. So vertical NAND is a starting point of how memory is starting to transition from planar to vertical. Eventually, for any of the emerging memories to also be successful, they have to increase the density and compete with NAND, and that's going to require vertical scaling for a lot of the emerging memories. So in conclusion, what I wanted to say is definitely NAND is changing, and the market is using NAND in very different ways with enterprise SSDs that we are looking at as well as consumer. In that whole spectrum, NAND is starting to enable a lot of new applications. With that, we are seeing a huge growth, and to continue to meet that demand, planar NAND has to transition to vertical NAND. It's not that we cannot make 30 nanometer planar NAND, we can today, but the performance of 13 or 12 nanometer planar NAND are going to be inferior compared to a vertical NAND performance. And the cost it takes to continue to shrink planar won't have the returns in terms of the density increase. And while there are a lot of new emerging memories that are coming up, they are all going to have their own niche in terms of performance. There's not a single memory that completely replaces all the things that a DRAM can do or all the things that NAND can do. And with NAND, vertical NAND in particular being the low-cost provider, NAND is here to stay for a long time. And some of these other memories are going to work in synergy with NAND and DRAM, but not completely replace either one of them. That's my last slide. With that, I would like to end the talk and maybe take a few questions.
Quick question regarding the TC-RAM. Micron is the only company last year that supplying TC-RAM. Do you see TC-RAM will stay in the niche application? Where's that?
It's back to what I was showing. We had a PC-RAM product that we still have in a small volume. It was supposed to get into certain mobile and low-cost applications, but eventually the density was not high enough, and it couldn't compete with the cost positioning of NAND, and the performance benefits that we were seeing was not significant enough. There's going to be continued innovations happening within the phase change, and there's probably different types of phase change memories that could still come into the market, but I still feel none of them are going to completely replace NAND. Eventually, you could look at a multi-chip package type solution where you take the advantages of NAND that it provides and then combine with any of these new emerging memories that have a unique performance benefit over NAND and use it in synergy to solve the solution problem.
Hi, Naga. Doug Resnick, Canada Technologies. Getting back to your point on emerging memory applications, I think you made the point that it's still going to have to be a 3D type of stacking in order to get the density. Do you think that that 3D architecture will look more like what's being planned for 3D NAND, or perhaps a crossbar arrangement? You have multiple levels that are crossbar.
It's a good question. It depends on the memory type. And again, when I say eventually has to be in a vertical stack, it's if you're wanting to compete with a NAND-like application. If you are wanting to just do the processing applications like DRAM, then you can just continue to scale, but eventually you're also going to hit the limits. Can you get one of these emerging memories to be 8 gig or 16 gig that DRAM can do and still deliver the same performance? It's not clear. On the vertical architecture, if there is any of these memories that are going to compete with NAND, then you're going to talk about 300 gigabytes or eventually a 1 terabyte type SSD drives. And for any of these emerging memories to be able to do that, they have to become vertical. And architecture-wise, it depends on which emerging memory we are going to talk about. To be a cross-point type application, you need to have different features within that memory, and that's going to be very difficult to find. So some memories might lend themselves to that architecture, while others might not. So it depends on which particular memory type that you're looking at.
At a recent conference in Monterey, Micron presented a very innovative concept in which the pillar was made from single crystalline silicon. And if that's so, that changes the nature of that 3D structure. Can you comment on that?
I haven't looked at the details of the presentation, so I cannot comment fully, but yes, it changes the vertical NAND structure completely if you can go make a single crystalline silicon pillar. But I cannot comment more without looking at the details of it.
Okay, well, thank you very much, Naga. That was a great talk.
Thank you.